Good evening, everyone. Welcome to the January meeting of the Naperville Astronomical Association here from Northeastern Illinois. Thank you for joining us. As usual, I want to let you know how to interact with our program this evening. If you have any questions that you have for our speaker tonight, feel free, if you're watching us on Facebook, to post them in the comments column, and our control room operator, Jim, will be watching that tonight, and we'll pass along questions to our speaker. If you're watching us via the club website, or you just prefer to use email, you can send us an email at questions@naperastro.org. And Jim's also watching that feed, and he will, again, call out any questions that are of general interest and pass them along to the speaker. There's not a lot else on our agenda this month. I did want to give the brief note that, as I've noted the past couple of meetings, we do have a YouTube channel going now where we're taking all of our past programming, all the other streaming sessions that we've done for meetings and programming, and our stargazing sessions, and we've put them up there. And the easiest way to find us there is simply to go to YouTube and search for the words Naperville and astronomy, and our channel, I'm sure, will come up fairly high on the list there. If you do happen to do that, and you could do us a favor and subscribe to the channel, it'll help us get enough subscribers that we can get a nice custom URL for it, rather than the rather long set of letters and numbers that we're currently using. On the upcoming events calendar, we have our fundamentals program for this month and our February program to announce. Our fundamentals program 2 weeks from tonight, on Tuesday the 19th, will be on helping any of you who might have gotten a telescope recently, maybe over the holidays or something, try to pass along some pointers to you on how to get it set up and get successful with it. So some really basic guidelines to answer questions that we often get about running a telescope for the first time. Things that to an experienced observer seem very simple, but can sure be frustrating if you're first trying to set up a telescope. So that's 2 weeks from tonight on the 19th, and this same channel, wherever you're watching us now. And then our February monthly program will be on a historical program on the Elgin Watch Factory Observatory in Elgin, Illinois, just up the way from us here. And that dates to more than 100 years ago, actually, when the observatory was put in to use for setting the master clocks at the watch factory. So that'll be an interesting historical program by the planetarium operator from the unit school district up there. So that's something to look forward to. Otherwise, you can always follow our website calendar for upcoming events. And if you follow us on Facebook, or if you're a club member and belong to them on the message board, we will post when we do any pop-up events. We're about due to get out and try to pass along some more live observing events, so we'll be doing that. This evening, we have a return engagement. If you were with us last summer, Larry Bartoszek gave a really interesting talk on the origins of the elements in the universe, and tonight he's returning to talk to us about a project that he actually helped build some of the equipment for, the Sloan Digital Sky Survey, which has been an amazingly productive astronomical undertaking. And I'm not going to try to give the program forward. Instead, I'm going to turn the screen over to Larry and let him present away. So Larry, it's up to you.
All right, so tonight we're going to talk about the Sloan Digital Sky Survey, and here's the outline. There's a lot of history to talk about here. The Sloan program has been running for over 20 years, and I drew a lot of the text and pictures for this talk from the many excellent SDSS web pages. And the last part of the talk will focus on the original 2.5 meter telescope at Apache Point that I helped build. So what is the Sloan Digital Sky Survey? The Sloan Survey is the most ambitious, it's the most ambitious astronomy project in history, actually. It's a multispectral imaging and spectroscopic redshift survey that started with one telescope, actually two telescopes at Apache Point, but one was just a spotter scope. 2.5 meter wide angle optical telescope at Apache Point Observatory in New Mexico. The project was named after Alfred Sloan. The Sloan Foundation contributed a significant amount of money. Data collection began in 2000, and Fermilab, where I used to work, designed a data acquisition system. And it has added more telescopes in other parts of the world to image more of the sky. So this is a Google map of where Apache Point Observatory is. It's on a mountain. You fly into El Paso and drive up to Apache Point in the mountains through the town of Cloudcroft. And when you're up at the observatory, you're looking down over Alamogordo, New Mexico, which is right in here, and the White Sands National Park, where the Trinity test site was for the first atomic bomb. It's really amazing. It's beautiful, absolutely beautiful territory. So this is a collection of pictures. This actually houses the pointer scope or the spotter scope. This is the house for the Sloan Digital Sky Survey. The house moves back and forth on rails and covers the telescope when weather is bad. And this is the telescope with John Peoples standing in front of it. John Peoples was a director of Fermilab, and he was also the third director of the Sloan Digital Sky Survey. So I helped Jim Gunn and the other people who were involved in the first installation of the camera, and I'll talk more of that later in the program. You can see how beautiful the landscape is. And actually, New Mexico is a free-range state, which means cows are allowed to roam anywhere they want to in the state. And it was this job on the Sloan Digital Sky Survey that taught me just how big and dangerous cows can be in the dark. When I pulled up to Apache Point Observatory for the first time, dead of night, I mean, because it's an observatory, no street lights, no nothing. You're supposed to park on the lower level. And I had an encounter with a several thousand-pound cow, and the cows in in New Mexico all have horns. So it gave me a respect for cows. So you might be asking, why did Fermilab get involved in an astronomy project? It's because astronomers had never collected data like this before. It looks like a high-energy physics experiment. The picture to the right is an image of the Sloan data flow, where data is divided up for different purposes and directed in different places. And then how much data does the Apache Point telescope collect? Well, every night when it's running, 200 gigabytes of data are produced, which is about 70 terabytes a year, which doesn't sound like that much. But remember, this is 20 years ago, where experiments collected much less data than they do now. Experiments at CERN, like Atlas, collect 3,200 terabytes per year. So there was a reason. I mean, there was a reason for Fermilab to get involved. They were familiar with designing data structures and pipelines and databases that could collect and use the data that the telescope was producing. So since it's been running for 20 years, there are phases of the Sloan Digital Sky Survey, so many names, and we're gonna talk about what each phase did. But from 2000 to 2008 was SDSS 1 and SDSS 2, which are now referred to as the Legacy Survey. The Supernova Survey and the Segway Survey started in SDSS 2. The very first Legacy Survey was only the Apache Point telescope, and it was spectroscopy where a single optical fiber determined the redshift for an entire galaxy. And I'll show you some of the upgrades that indicate that that's no longer the case now. Now, all of the Sloan web pages are still available, and all of the data is available to the public. And I'll show you what that looks like in a moment.
Hey, Larry, we had a Facebook question come in.
Okay.
Tony Harris asks, is that the same Jim Gum from Palomar and the first book in the
Yes.
book First Light.
Yes, it's exactly him, and he is such a character to work with. Yes. Yeah, Richard Preston's book. And well, we're going to talk about Palomar for briefly also. So here are some of the websites. The surveys 1 and 2 are encapsulated in the classic SDSS website, which is not updated but still available. SDSS 3 has BOSS, Segway 2, APOgee, and Marvels. That's no longer updated also, but all that data is still available. SDSS 4 was running until 2020 with EBOSS, which was divided into spiders and TDSS. I actually don't put any data in for spiders and TDSS, but I do cover EBOSS, APOgee II, and Manga. And then we'll talk about the future of Sloan from 2020 on with the Milky Way mapper, the black hole mapper, and the local volume mapper. So what was the legacy survey? Well, the original observing plan resulted in a uniform, well-calibrated map of the universe, and it will be used for decades. This map replaces the glass plates that were created in the 50s at the Palomar Observatory. And you can go to sdss.org and begin to view the pages, and I did that to see a comparison. Sloan has a page that has a comparison between the new SDSS data and the Palomar Observatory Sky Survey, which was done in the 50s. So in this article that I refer to at the bottom of the screen, there are instructions for how to access the Sky Survey Navigator for SDSS, and it tells you to go to an object called PAL3, which is a globular cluster, and this is the image that it goes to. And it also gives you instructions on how to access the same image from the glass plates from the Palomar Observatory. But when I did that, and I'll show you in a second, I could not tell that this image was the same as that image until I zoomed out 2 steps. Now there's that image, and I'll flip to the next slide. You can see that that image is the same as this image, which comes from the glass plates from Palomar from the 50s. And what they've done, the Palomar plates have been digitized, and they are also available on the web, but there's just far less information available. There are fewer zoom steps. I mean, as you can see, you can get rather intimate with the data, but one of the big differences is color. The Sloan data is in color, and you can really distinguish different things. For example, this object right here may or may not be a binary star system. You can't really tell what it is when you zoom out, and you certainly can't tell what it is from the Palomar image. And this is what the Palomar webpage looks like when you're trying to retrieve an image and navigate through it. So it's not quite as friendly. In the Sloan page, you can, and actually, if anybody knows out there, I'm curious to know why east and west are inverted on the screen. Why isn't east on the right and west on the left? North and south seem to be natural, and I think it has something to do with the way you look up in the sky, but I'm not completely sure. So if anybody knows the answer to that, I'm interested. So the data for Sloan can be represented as the orange spider. And there's something to take away from this data, a number of things to take away. The top image shows a zoom in all the way to a tiny portion of a galaxy in M33, which looks like a globular cluster, actually. And the spider, if you look at the data, what you see is the structure. This is large-scale structure in the universe, and we're going to talk about this large-scale structure because it's real. There are voids and walls of galaxies in the universe. And this is another image of all of the galactic data from Sloan from the Legacy Survey, where the image is color-coded so that red indicates dense areas of galaxies and green indicates less dense areas of galaxies. And you can clearly see the walls and the voids in the universe. And we'll talk in a moment about where does that structure come from, because that was one of the big mysteries of astronomy for a while. So now let's talk about the Supernova Survey that started in SDSS II. In 1998, the original Supernova Survey discovered that the universe's expansion wasn't uniform, and it wasn't slowing down. It was actually speeding up, which was the reason for the theory of dark energy. So the Sloan Survey from 2005 to 2008 looked at one stripe of sky along the celestial equator and discovered more than 500 type 1a supernovae. And the type 1a is critical because originally we thought that type 1a supernovae were all made by the same process and thus had the same luminosity. So they represented a standard candle in the universe where if you knew how bright the supernova was and you knew it was a type 1a supernova, you knew how far away it was by its distance from its luminosity. And its redshift then tells you also something about how far away it is. And that's how the difference between the luminosity and the redshift led people to understand that the universe's expansion is accelerating. So here's an image from Sloan of the over 500 supernovae that it gathered from 2005 to 2007. And it shows how each image is centered on the supernova, which usually is brighter than its entire galaxy that it's with. But there's a caveat. Also, based on work from the Sloan Digital Sky Survey, we have discovered that type 1a supernovae can be produced through different mechanisms. And the downside of this is that it might lose its standing as the standard candle for measuring galactic distances. This could change our understanding of dark energy. There are also new models of the expansion of the universe that predict the expansion without invoking dark energy, which I also find very interesting. So SEGWAY, the Sloan Extension for Galactic Understanding and Exploration. SEGWAY is one of the surveys that was dedicated to understanding the structure of the Milky Way. Several of the Sloan surveys were looking at the Milky Way in specific. Several were looking at the large-scale structure of the universe, and SEGWAY was one that was focusing on the Milky Way. And it obtained spectra from nearly 230,000 unique stars over a range of types to investigate the structure of the Milky Way. So one of the things that you learn by looking at the spectroscopy of stars in the Milky Way is something called metallicity, the metal content of the stars. And what we see is that when you're far away from the midplane, the amount of metallicity is different than when you're close to the midplane. And that says things about the history of the stars and objects throughout the thickness of the galaxy. And one of the things they thought is that objects that are further away from the midplane of the galaxy were accreted later. So then we get into SDSS 3, 4 simultaneous survey, a continuation of SEGWAY, a new one, BOSS, the Baryon Acoustic Oscillation Survey, MARVELS, which was a planetary survey, and APOgee, which was another survey for galactic evolution. So APOgee is high resolution, high signal to noise, infrared spectroscopy to penetrate the dust that obscures significant fractions of the disk and the bulge of our galaxy. So APOgee surveyed over 100,000 red giant stars across the full range of the galactic bulge and the bar on the disk and the halo. BOSS. This one is particularly interesting to me because the baryon oscillations give you an idea of the large-scale structure of the universe. And if you're not familiar with baryon acoustic oscillations, during the Big Bang, there had to be sound waves caused by quantum fluctuations when the universe was very tiny and very hot in the original plasma of the Big Bang. And these sound waves propagated through the early universe like ripples in a pond, and they are what gave the characteristic scale to the fluctuations. Think of it as fluctuations like sound is changes in the density of the air. Well, this is sound waves in the plasma of the early universe. So places where the plasma is denser, the dark matter accumulated in those denser areas, and that dark matter led to the walls of dense areas of galaxies. So it's these very early ripples. On the left, you see an artist's impression. Actually, it's not an artist's impression. That's the cosmic microwave background, where the temperature fluctuations are on the order of 300 millikelvin. There's just an incredibly uniform cosmic microwave background radiation coming from the Big Bang. But that variation in the cosmic microwave background was also caused by these baryon acoustic oscillations, the sound waves that spread through the early universe and led to the large-scale structure of the universe. So I'm completely fascinated by the large-scale structure aspects of what Sloan accomplished. Marvels is a lot like Kepler in the sense that it was designed to look for exoplanets. So it has very good sensitivity, and so it's an Earth-based program similar to what the Kepler telescope is doing in orbit around the sun, and it was able to find planets around stars and looking in things such as the brown dwarf desert, which I didn't take the time to look up. I'm not completely sure what the brown dwarf desert is, but presumably it has something to do with large planets in orbit around a certain type of brown dwarfs. Segway 2 took the data from Segway 1 and Segway and 2 and revealed the complex kinematic and chemical substructure of the galactic halo and the disks. So this provides clues to the history. How did the galaxy come together billions and billions of years ago? And the outer halos, where the globular clusters are and other things, are expected to be dominated by the late time accretion events. So things that happened later in the history of the galaxy. And Segway then constrains existing models for the formation of the stellar halo, and it informs the next generation of high-resolution simulations of galaxy formation. And then it can also uncover rare, chemically primitive stars that are the fossils of the earliest generations of cosmic star formation. SDSS-4, which was completed just last year, added data from the southern hemisphere. So one of the surveys in SDSS-4 is called APOgee II, and this is a stellar spectroscopic survey of the Milky Way, but this time using an additional telescope down in Chile. And I almost got an opportunity to work on that one, and they just didn't need me, so I never went down there. But I would have loved the opportunity. So the fourth phase of SDSS uses two telescopes, one at Apache Point and the other at Las Campanas in Chile, and it can see the entire Milky Way. So EBOS is a continuation of the baryon oscillation spectroscopic survey, and what they did there is they observed galaxies and quasars in a range of distances that at the time were completely unexplored by other three-dimensional maps of the large-scale structure. So in filling this gap, EBOS created the largest volume survey of the universe to date. And this gives you an idea. This shell represents the very beginning, the Big Bang and the cosmic microwave background. So from 3 to 8 billion years after the Big Bang, the shell that EBOS is looking at is in here. So it's after the Dark Ages, and there's intergalactic gas, and it's the onset of dark energy. So it's the change of when the universe stopped slowing down and started to accelerate. And this was the first time I'd seen the expression the Lyman alpha forest, which is a distribution of absorption lines coming from transitions in hydrogen, where the electron drops down to the ground state. But the light that's coming from hydrogen, which is very easy to characterize and identify, is passing through multiple gas clouds with different redshifts on its way here. And this causes a proliferation of Lyman alpha lines that have to be sorted out. So Manga, this is the one I was telling you about in the beginning survey, in the legacy survey. One optic fiber calculated or determined the redshift for an entire galaxy. Manga was an upgrade that allows more than one optic fiber to collect lights from a single galaxy. So you can see the image of a galaxy on an array of fiber optics. So you can actually measure the redshifts of different parts of the galaxy. And you can measure the spectra coming from different lights, different parts of the galaxy. So this was a really amazing upgrade to the spectroscopy of the Sloan survey. And the future of SDSS. So there will be several surveys, the local volume mapper, the black hole mapper, the Milky Way mapper, using multiple telescopes, multiple bands, multi-object fiber spectroscopy. Yeah, there was an expression here somewhere that talked about epochs of spectroscopy. I may have deleted it because I simply didn't know what it meant. So the Milky Way mapper targets 4 to 5 million stars across the Milky Way, collecting infrared spectra with the APOgee spectrograph and or optical spectra with the BOSS spectrograph. And it seeks to understand the evolution of the Milky Way, the physics of the stars, the interstellar medium, and the architecture of multiple star and planetary systems. The black hole mapper, here's the expression, multiple epochs of spectroscopy, which I copied directly off the site. So if anybody listening can tell me what multiple epochs of spectroscopy means, I would love to know the answer to that. I was unable to determine what that means. For more than 300,000 quasars, to understand the masses, the accretion physics, and the growth and evolution over cosmic time of supermassive black holes. It will use the existing BOSS spectrographs and has the spectral resolution. The higher the spectral resolution is, the better the resolution is. So 2000 is a relatively high number and higher than it used to be in the early days of the spectroscopy. And it will operate at both the north and south telescopes.
Hey Larry, we have a Facebook question.
Okay.
Eric Clays asks, does the upgrade to the Manga allow us to determine which way a galaxy is rotating?
Yes. The differential redshift does allow you to see which way the galaxy is rotating. Absolutely. And actually, we have to make that correction in observations of our own galaxy, because there's a very small redshift from the rotation of our galaxy. And so that is a correction that has to be made. So the local volume mapper is going to look at the Milky Way, the small and large Magellanic clouds, which of course you can only see from the southern telescope. There are new spectrographs that have been built, and the resolution of the spectrum is also higher now at 4,000 wavelengths. And it will cover 20 million contiguous spectra over 2,500 square degrees of sky. So I've discussed the history of Sloan, but now I want to go back to the very beginning of how did we build the very first telescope and what does it look like? So the first paragraph there, a modified 2-corrector Ritchie-Chrétien design with a 2.5 meter f2.25 primary, a 1.08 meters secondary, a Gascoigne astigmatism corrector, and one of a pair of interchangeable highly aspheric correctors near the focal plane, one for imaging and the other for spectroscopy. That paragraph comes directly from the paper. My name is on that paper for the building of the telescope. This gives you an idea of what a Ritchie-Chrétien telescope looks like with the camera underneath the primary. What it looks like in reality is that, and the box that is around the telescope is a windbreak, so that the wind doesn't cause the mirrors in the optical chain to move. Because the winds on top of the mountain at Apache Point can be pretty impressive. And so this is putting the camera on for the first time. So this is the very first time that the latches that I designed for the telescope were tested with the real camera. Now, what's special is this camera was 120 megapixels, and it's a drift camera, which means that the telescope is not taking still images. The telescope is moving across the sky at a different rate than the objects in the sky are moving. And that's to allow the same image to cross the different CCD planes where different filters are used. So the image is reconstructed from a moving picture, basically. And this back 20 years ago, this was a big deal. This camera cost $4 million and was 120 megapixel. We've just in the last couple of years built a new camera for the Dark Energy Survey. That the camera was built at Fermilab, and that's 570 megapixels. So its data collection rate will be more than 5 times Sloan's data collection rate. So there's some serious pixels coming through. So what was my role in the Sloan telescope? I was hired by Fermilab in December of 1996 to debug and finish the design of the latches. The latches are pneumatic clamps. There are 6 of them that hold the camera and the spectroscope to the bottom of the telescope. And Jim did the original design for the latches, but they didn't work. When the shop manufactured the first one, it jammed. And that's because I discovered that Jim had put too many belts and suspenders in the design of the latches. I simplified the design. I basically just took parts out, and the latches worked, and we tested them in a freezer at Fermilab to make sure that they were reliable for the coldest temperatures that were likely to be seen on the mountain. And that's what a latch looks like. It's a very simple mechanism where this is the part that grabs onto the camera. There is a pneumatic cylinder, which isn't shown, that the piston has a roller on it that pushes against the bottom of the swing latch and thrusts this out. And the piston basically locks against this detent when the latch is completely rotated out. So even if the pneumatic piston loses air pressure, it still stays in place because the roller is basically locked by that detent. And when the air pressure is reversed to pull the piston back into the pneumatic cylinder, the spring helps forces the retraction, actually. So I had to come up with some bearings and some other things and perfect the design and make it work and test it. So unfortunately, I don't have photos of the original test fixture in the freezer at Fermilab, but this is what it looked like, where the latch was being tested against a stack of springs that simulated the same springs in the camera mounting. And we had all kinds of problems with the original alloy that the latch was made out of. Some of the coatings that they thought would be useful turned out to be less than useful when they flaked off. They basically wore off from the roller running back and forth on the latch. But eventually we got it right. And that's what the latches look like on the bottom of the telescope. And it took me a couple of days to pipe them in place, looking out over the mountain the whole time. It was a blast. I really had a lovely time with that job. So what was the process in the legacy survey? The process is the telescope would scan across the sky, recording images with the optical CCD camera. And astronomers would look at the images and they would select which objects they wanted for spectroscopic analysis. And then a plug plate was made, which took the place of the camera and had holes in the plug plate where each object would appear in the sky. And the holes were individually drilled. There are hundreds of these plug plates. So the camera is taken off, And the spectroscope was mounted on the camera with optical fibers that are plugged into each hole in the plug plate individually. And so whatever object it lines up with that hole in the plug plate could be separately analyzed. So that's how you collect the spectra of hundreds of different galaxies on the same night at the same time. So on the following night, then, the telescope would look at the same patch of sky with the spectroscope and observe the light of each object separated into its spectrum and further separated by each fiber optic. So this is what the process looks like of connecting the spectroscope to the plug plate. It had to be done manually or by a person. And then they used a test laser to map what was plugged into what so that they knew which position on the plug plate corresponded to which set of optical detectors on the spectroscope. So after 20 years, what did they have? Sloan produced the largest, most detailed 3D map of the universe so far. They filled a gap of 11 billion years in the expansion history of the universe, and they provide data which supports the theory of a flat geometry of the universe. Sloan also confirms that different regions seem to be expanding at different speeds. And finally, they created the most detailed three-dimensional map, and they created the first map of the dark matter, which is what comes out of understanding the voids and walls in the universe. And they made all that data available to the public. And that is basically all I have. I'm happy to take questions.
I don't think we have any more questions. We did have someone comment that in astrophotography or in astrophotographs, east is usually on the left as you're looking south from the northern hemisphere. So.
Okay, I can see.
I think you're basically right. If you're facing south and you look up, your north-south or your east-west would be that direction.
Okay. Yeah, I see it. One of those weird things about looking up instead of looking at a map.
Right. I don't see any other questions, and we don't have any questions in the email. So the moment that we stop talking, 12 questions will come in. But as of right now, there's nothing else. So I guess we can flip back to you, Drew, if you're ready.
Thank you very much, Larry. It's always interesting to us to hear some inside story about things. So we have to remember that all the interesting things we're always hearing about are done by real people out there. So go ahead.
Drew, this is the first time I've given that talk since I created it over the past couple of months. And I'd be very interested in feedback as to whether or not it covered material that was interesting, and if I covered it at the right speed. I may have gone a little fast, I'm not sure.
Well, so viewers out there, that's an invitation to you. If you send us anything, any of your comments, again, either via Facebook or via email to the club, we will pass them along to Larry. So if you want to cogitate about it a little bit and write down something tomorrow morning, if you send it to us, we will pass it along to Larry. So thank you very much, Larry.
You can also make a PDF of the talk available if anybody wants to check some of the links out. Or
okay, if you would like to get that to us, we'll put it on the message board for members to access. If we do that, we have a file there for presentations that
okay,
speakers who want to pass them along. That's great. Again, thank you very much. That closes things out for us.
Drew, we had one question come in for Larry.
Okay.
During Kathy's there. It's a good question. So Vincent asks, is the SDSS project well funded? Will we see results for years to come?
As far as I can tell, yes. It certainly has been approved. I noticed when I went to the website and saw the phase 5 work, it doesn't say when it's supposed to terminate. So it starts in 2021 and continues, and I don't know for how many years the last few projects have been funded for. But as far as I know, yes, there will still be more work for years. And the data that's already been produced, it still needs to be analyzed and is the work of students for more than a generation, I'm sure.
Okay, thank you, Larry.
Okay, well, that finishes things up, as I hope it says on your screens right now. I hope I'm sharing the right screen. For members, if you would like to join in our virtual after meeting socializing, there's a Zoom meeting. It was the same one we've used in past months. So there's
it's actually different from
oh, that's right. It was different last month, I guess. This is the one that was that Jim posted in the message board. So the one that I've got up on the screen now. So the link that Jim posted already in the message board about a day ago is the place to go. And otherwise, we're going to adjourn for the evening. And like I say, if members want to join us there, we will get to chat a little bit more about things. Larry's welcome to join us too if he wants to come and sit in our virtual pub. So anyway, I hope everyone has enjoyed the presentation. Do please keep an eye on what we're doing in the future and join us for future things. Otherwise, for tonight, we're signing off. Thank you very much and keep looking up.